Okay, in this example, we're not doing much different than what we did last week, except for now we've got two things that are combined together. So I've got 1 molar of hydrocyanic acid, and there should not be a little negative up here, 5.0 molar of nitrous acid. Are either of those acids strong? No. Okay, the process here is that they're both weak. And so we've solved for the pH of a weak acid already, but now we just have two things that are being combined together into one big solution. So what you need to do, since they're both weak, is set up an ice table for each one separately, solve for X for each one, and then add them together for the total hydrogen ion concentration to calculate the pH. Okay, so it's really just doing two problems in one and combining it together at the end. So for my HCN, I'm going to have hydrogen ions, cyanide ions, a little bit, small percentage of dissociation. My starting concentration here is 1 molar. Yep.
Would you determine the main producer of hydrogen ions when they use that one?
Not if they're both weak. If they're both weak, then you have to take into consideration both of them together. When you have one strong and one weak, then the strong one overpowers the weak one. That's the next example I'm going to do. And so you just take into consideration that one. But when they're both weak, you need to do hydrogen ion concentration of both. So let's see. Over here, I'm going to have plus X on each. Over here, minus X. So 1 minus X. And you would look up your Ka values on the ice table, or on the, the Ka table, which is on page 628. 628. If you want to write that down, again, is your Ka values. So the Ka value for hydrocyanic acid is 6.2 times 10 to the negative 10. Okay, that's Ka. Just looked it up. And then that's going to be equal to, I'm going to set up my equilibrium expression, my Ka expression, with my hydrogen ion concentration, cyanide ion concentration. So I'm going to end up with X squared over 1 minus X. That's small. That goes away. I'm not going to spend a lot of time talking about solving for X because we've solved for X a lot. It's the process of putting everything together at the end. So X equals 2.5 times 10 to the negative 5 molar. That's the hydrogen ion concentration. That comes from the hydrocyanic acid. Then I need to do it again for the nitrous acid. So I'm going to set up that ice table. Gives me hydrogen ions, nitrite ions. There we go. My starting concentration of the nitrous acid is 5.00 molar. This is 0, this is 0. Plus X plus X. These all start to look very similar. Minus X, 5 minus X. Look up the Ka value for nitrous acid is 4.0 times 10 to the negative 4. That equals X squared over 5 minus X. That goes away. X is equal to 4.5 times 10 to the negative 2. That's the hydrogen ion concentration. And what do I do with those two hydrogen ion concentration numbers? I add them together to get the total amount of hydrogen ions in that solution, of them being all combined together. So then the total is, I should write total here. Total hydrogen and ion concentration, when I add those together, oh, it's super small. It actually doesn't change very much. 4.5 times 10 to the negative 2 molar, which is really this one. comes from the stronger acid, because this one has such a small Ka value. The smaller the Ka value, the weaker the acid actually is, and the smaller the amount of dissociation. So then the pH is equal to the negative log of that, 4.5 times 10 to the negative 2 equals 1.35. Just pH. On the next one, I'll let you write that down. Okay, in this problem, let's see, I've got 25 milliliters of 0.25 molar nitric acid mixed with 250 milliliters of nitrous acid. Now, the thing that you can notice here is that you have nitric acid and nitrous acid. One of them is strong and one of them is weak. And so when you have a combination of one that's a whole lot stronger than the other one, then you can just take that one into consideration and forget the other one completely, because the amount of hydrogen ions that are added into the solution from this is going to be so small compared to the hydrogen ion concentration of this that it doesn't really matter. In the one that we did previously, it didn't really matter either, because this Ka was so small, but if they were similar Ka values, it would make a difference, which is why you have to calculate them separately. But here, what you should know is that whenever you have a combination of a weak acid and a strong acid, that the strong acid always wins. And so that's what you use when you're doing your calculation. Now, the only thing about this is you can't just take your concentration and negative log it. Since you have two things being combined together, you have to figure out what the new concentration is with the total volume. And so in this case, I have 25 milliliters of nitric acid, 200, I think I just want this to be 25.0, plus 25 milliliters of nitrous acid, so my total volume is 50 milliliters. So then, in order to figure out what the concentration is of the nitric acid in that solution, I've got to do M1V1 equals M2V2. So I have my 0.25 molar concentration of the strong acid, 25 milliliters of it, and I want to figure out what's the new concentration in a 50 milliliter solution. So that M2 is really what I'm finding is the concentration of the nitric acid, but it's also the same thing as the concentration of hydrogen ions, because it's a strong acid and it basically fully dissociates. So that M2 is equal to the hydrogen ion concentration, which is 0.125. And then pH equals the negative log of that number, which is 0.903. Questions on that one? If you see one that's strong and one that's weak, then you forget about the weak one, except for you use the volume of it to figure out the new concentration of the strong acid with the new volume. All right, next example. We're moving on just a little bit from weak acids. This is NH3. Is NH3 an acid or a base? It is a base. And so the process is the same. The only difference is that when you're dealing with bases, you go through and calculate hydroxide ion concentration first and then work kind of backwards to get pH. When you write the reaction for this one, you have NH3 plus, and when you have ammonia reacting with water, it's helpful to write water this way because when you have the reaction take place, you end up with NH4. So one of those hydrogens comes over there, hooks onto NH3, and then you're left with hydroxide ions, which is the key thing that makes it basic. So I'm going to go through and do a whole very similar to what you did with a weak acid, where you set up the ice table here. I know that the initial concentration is 0.25 molar of NH3. Does anything in the water column matter? Nope. Water's liquid. NH4 is aqueous, hydroxide aqueous, this is aqueous. In our equilibrium expression, it's only the aqueous stuff that matters. The liquids are left out, and so the water is left out of that. So I don't need to fill out anything there. Initial concentration of NH4 is 0. Hydroxide is 0. Plus X, and minus X over here. Now, since it's asking me to calculate the pH, I need to figure out, well, since I have hydroxide ions here, I can figure out the pOH, and then I can subtract it from 14 to get the pH, but I need to figure out what the hydroxide ion concentration is. Now, remember that table that I didn't tell you about of Ka values? There's also a table of Kb values right here on page 647. And we haven't really talked about Kb so much, but it's really the exact same thing as Ka. It's just specific to the reaction, the equilibrium expression for bases instead of acids. So Kb values are on page 647. If you're dealing with a base, you need to look up the Kb value for NH3, which is ammonia. When I look up, and it tells you right here, the formula for the base is NH3. Its conjugate acid is NH4 plus, because after it gains the hydrogen from the water, we drew that. And then the Kb is 1.8 times 10 to the negative 5. So I'm going to use my Kb value and set it equal to my equilibrium expression to solve for X. So it's X squared, products over reactants, X squared over 0.250 minus X. That cancels out. My X in this is equal to 0.0021, which equals the hydroxide ion concentration. If I negative log that number, 0.0021, it gives me 2.68. That's the pOH. What can I do with the pOH number to get pH? Subtract it from 14. So 14 minus 2.68 equals 11.32. That's the pH, which makes sense because this is a base, so you should have a basic pH value. Questions there? Same kind of deal, just using a KB value instead of a KA. Different kind of setup of the dissociation that's taking place. It's the water that dissociates here. All right, let's see. All right, this is going to be the last one, number 6, actually, because this example, letter C, calculating Ka from a percent dissociation, that was, I just did that homework problem. So that was number 65. So I just did that one with you guys, so I don't have to do it as the example today, where you're given the percent dissociation and you can go backwards and figure out what the Ka value is. Or you could do the same thing if it was like a KB or something like that. So for number 6, key things, 25 milliliters of 0.25 molar potassium hydroxide, 25 milliliters of 0.25 of that base, whatever that's called. First of all, you should recognize what kinds of things you're dealing with. You guys have the strong bases memorized, right? Potassium hydroxide is strong. This one is not one of the strong ones that you memorized, so therefore it's weak. So just like the strong acids, when you had a strong one and a weak one put together, the strong one wins basically, and you just calculate hydrogen ion concentration from that. The same thing happens with bases. If there's a weak base, then you don't take that into consideration at all. So again, well, you take it into consideration to figure out the new concentration by doing M1V1, M2V2. So the strong base wins. I want to figure out what's the new concentration of the strong base with the new volume. So same process. My initial molarity of the strong acid is 0.25. Initial volume of that is 25 milliliters equals M2 times 50 milliliters, which is the volume of the solution when it's combined together, the mixture of those two. M2 equals 0.125 molar. That's the concentration of hydroxide ions. So really, the problems that you're dealing with bases, they're exactly the same as the ones you're dealing with acids. The only difference is that when you solve for X, or when you solve for the concentration, it's hydroxide ions. So you end up with one extra step because when you negative log it, you get the POH instead of the pH. So the POH equals the negative log of 0.125. That equals 0.9. And then I just have to subtract 14 minus 0.9 to give me the pH. It's 13.10.